Hi kids, this is the second video in our electricity unit called Conservation of Charge and Charging. The essential question for this video is, how do objects end up with an unbalanced sigma charge? So just a quick reminder from the last video, charge is a new variable for us. We use a Q to represent it. The units of charge are the coulomb. And the vast majority of charged particles in the universe are protons and electrons. Those are the two we're most concerned with. Protons have a charge of positive 1 coulomb apiece, and electrons have a charge of negative 1 coulomb apiece. So the main point of this video is on the processes we call charging, which means changing the sigma q of an object. Making the charges unbalanced in our object. As a reminder, objects in our universe usually start with a balanced number of electrons and protons. So you and the desk and then everything around you have the same number of electrons or protons, and protons probably. So an object or system gets charged when the electrons move in or out of the object. Reminder that protons can't move, so we have to get positive or negative charges only by moving electrons without touching our protons. The total charge in a closed system is conserved. So in the universe, we have 0 sigma charge. All the protons are balanced out. And that's usually true at a small scale as well. So if I have two objects and they start off with neutral, they start off with the same number of protons and electrons, we're going to move charges around, but the total charge in that system is probably still going to be 0. It's just that now those charges have a different distribution. So there are 3 different ways to get a sigma charge on an object. The first is called friction charging, and this is probably the one that you guys are most familiar with in your life if you've ever played around with electricity. You know, you've scuffed your foot on the carpet and then zapped your little brother or something. You were using friction charging to get a unbalanced charge on an object. A couple key aspects about friction charging: it requires rubbing, so just touching something won't charge it up. You actually have to rub the things together. And you have to, this only works with insulators, and specifically you have to have different insulators. So when you rub 2 different insulators together, we can get a charge. Sort of a drawing diagram. So this would be 2 different insulators. I have a green one and an orange one. They're both neutral to start, so the sigma q for the whole system and for the individual objects is 0. I have the same number of electrons and protons on this object. When I rub those 2 insulators against each other, what happens is that just by virtue of them being different materials, one of those materials has a slightly stronger desire for electrons than the other. And when you rub them together, what you're really doing is bringing all the little nooks and crannies and surface area of the insulators into very close contact, close enough that one of those atoms from one of the insulators can actually reach over and snag some electrons from the other one. So you'll notice that that orange insulator wanted electrons more than the green one did. So as they were rubbed, the orange one grabbed the electrons. Now, it didn't just grab any old electrons. Because these are insulators, it was only grabbing the electrons that were on the surface. It could only grab the closest electrons. Those electrons can't flow or move around the objects once they're there. So it grabs them from the surface of the green one, and those extra electrons are stuck basically on the surface of the orange one. However, if you wanted to figure out the sigma charge of those 2 insulators now, you'll notice that green has lost 5 electrons, so we took away 5 negative signs, which means that sigma q is now positive 5 coulombs. The orange one gained those 5 electrons, and so it has 5 extra negatives, which makes the sigma q negative 5 coulombs. Of course, if you add those together, you still get a sigma q of 0, and that's because charge is conserved. There's no particular easy way to determine which insulator is going to steal electrons from which other insulator. It's all been just determined experimentally. So scientists have rubbed a bunch of things together and then figured out who got the electrons. But there is something known as the electrostatic series, which is kind of our experimental evidence of which insulators really love electrons and which ones don't care about them as much. So that list shows in order from top to bottom the insulators that want the electrons the most. So rubber really loves electrons more than plastic, more than cotton, fur, wool, etc. And glass is an insulator that really doesn't care too much about electrons. So it's really easy to steal electrons off of glass. The reason why this is useful is because you can figure out, if I rub two things together, which one ends up getting a negative sigma charge and which one ends up being positive. So if I rub, for example, cotton on glass, the cotton ends up negative and the glass is going to end up positive. But if I rub cotton on rubber, the rubber ends up negative and the cotton ends up positive. So you can actually get different charges on the same insulator depending on what the other object that you rub them on is. Now, of course, I mentioned that they had to be different insulators, and that might be something to think about. We'll talk about it in class. But if I rub cotton on cotton, you can think about what might be happening and why you can't actually charge up cotton by rubbing it on a different piece of cotton. The second kind of charging is called contact charging, and contact charging happens when you have two conductors and you touch them to each other. These conductors need to start off with unequal sigma charge, so my system might have an unbalanced sigma charge to start, or maybe it's balanced but they're equal and opposite. And when you touch those two conductors, what happens is the electrons are going to flow because they can move easily until both conductors have the same sigma charge. So the electrons basically want to spread out as far as possible, so they spread out until they're balanced. You can also determine that the final charge of each one is going to be the average of the two original charges. Let me show you how this works. So let's say I have a blue conductor and a green conductor. The blue one has a sigma charge of +6. It has 6 extra protons. And the green one has a sigma charge of +2, so it has 2 extra protons. When you bring them into contact, because those electrons can flow, you don't have to rub or anything, you just have to touch them, and the electrons just spread out as far as they can. So before they were touching, the electrons in the green one were a little bit crammed, right? They'd rather have more space. The more space, the better, because they're repelling from each other. So when they come into contact, they spread out as far as possible. What happens is the final sigma q of each one is going to be the average. So 6 plus 2 is 8, divided by 2 is 4. That means when we're done, sigma q is +4 for each one. You can confirm that conservation of charge still works if you think about what moved and how many and in which direction. For that blue one, if you look at just that one, it went from a charge of +6 to a charge of +4. The way it did that is it gained 2 electrons. So if you add 2 more negatives, you go from a 6 to a 4. The green one went from a 2 to a 4, so it obviously got more positive. The way it got more positive was by losing 2 electrons. And so you'll notice that charge is conserved. One of them gained 2 electrons, the other one lost 2 electrons. I still have the same total number of protons and electrons in my system. I didn't gain or lose either of those things. You may have heard the term grounding or electrical grounding before. Electrical grounding is kind of like contact charging, but it's a contact between an object and the Earth. So the Earth is also a conductor, so it can do contact charging also. But what's kind of special about the Earth is it's so enormous. It has virtually limitless ability to either provide or absorb electrons. So whatever object you touch to the Earth can absorb extra electrons, or if that object needs electrons, it can provide those electrons. So what it means is that electrons can flow either to or from the Earth. A note about grounding: the electrons don't always end up balanced when we're done for various reasons that we'll talk about later on. But if you hear grounding, it's basically contact charging between the Earth and another conductor. Your houses are grounded because it provides a route for extra electrons to escape into the Earth, which is a safe place for them to go. That third prong on certain outlets in your house is connected literally to a stake that is drilled into the ground outside of your house, and it provides a lot of protection from extra electrons, which are dangerous for electronic devices, and they're also dangerous for you. So if your house gets hit by lightning, for example, those extra electrons are going to go into the Earth around your house instead of going into people or electronics or other things that might be problematic. The third kind of charging is known as induction charging, and it's definitely the most complex, takes the most steps. Induction charging involves using the two processes that we talked about earlier, polarization from the last slideshow, where you divide a neutral object into two halves, one positive and one negative, and also the process of grounding that we talked about just a minute ago. And so it uses those two processes to give a sigma charge to a conductor. The reason induction charging is really important is because you can actually charge something without touching it. And for the other two kinds of charging, you actually had to bring the objects into contact. So this is the most useful kind in the real world because you don't actually have to touch things to get them charged. So induction charging starts off with a neutral conductor. So that's a metal ball on top of some kind of stand that's holding it up. And the first step in induction charging is the polarization step. So you have another object that's gotten charged some other way. So maybe that's been friction charged. That rod on the left has a negative sigma charge. And you're going to bring it close to your conductor that was neutral. And what should happen is that conductor is going to polarize. That picture isn't actually that accurate because it shows the protons moving, which they shouldn't. But in any case, the protons, the left half ends up more positive and the right half ends up more negative because the electrons moved away. So it's still neutral, that conductor, but it now has a positive half and a negative half. The next step is the grounding step. So I now take a wire and I connect my conductor to the earth. And the reason that's significant is because those electrons in that conductor were basically trying to get as far away as possible from that rod, right? They were being repelled by the rod. And when I connect the earth to the conductor, they now have a place to go that's way further away from the rod. They can go like into the earth and then the other side of the globe if they want. So when I connect it with that wire, all those electrons from the conductor go onto the earth. They escape off of the conductor and onto the earth. And what that means is that the conductor is now left with just its protons. Okay, now we know we didn't have to ever touch it with that that rod, but all that's left is the protons. So when I move the rod away, the whole conductor ends up positive. So we've used polarization and grounding to give an unbalanced sigma charge to that conductor. All right, so that was a lot of information. I would definitely recommend that you go back and revisit the essential question, which was how do objects end up with an unbalanced sigma charge? And hopefully you now see there's lots of different ways depending on whether we're conductors or insulators or if we're touching or rubbing or not. As you go back and think about it, please focus on what are the three ways to charge an object, what materials can be charged using each method, and how does the concept of conservation of charge illustrated in each method.